Hello and welcome back to the series. Today we are tackling a fundamental decision every ML practitioner faces, choosing the right algorithm for your model. Specifically, we'll be comparing linear trainers versus tree-based trainers. If you've ever wondered why a simple linear model might outperform in certain scenarios or vice versa, this video is for you. Linear trainers like logistic regression excel in speed, interpretability, and handling straightforward relationships in your data. On the other hand, tree-based trainers such as decision trees or random forests shine when dealing with nonlinear patterns, interactions, and high-dimensional datasets, often delivering superior accuracy but at the cost of some complexity. In this episode, we'll break it down step by step, exploring real world use cases, walking through code examples, and benchmarking their performance on our sample dataset. By the end, you will have the insights to pick the best trainer for your next project. So, grab your coffee, fire up Visual Studio, and let us get started. In Visual Studio, find the method build and train we've defined in the last video about feature engineering. And as you see, we have a tree-based trainer, the fast tree algorithm, and we train a model, a classification model on three columns or three features, home and away teams, and the fair prop and the derived feature. And the new code is a second pipeline, a linear-based trainer, LBFGS logistic regression, which is a binary classification trainer. And um, as done in the fast tree, it builds or it is based on the base pipeline, so the same three features. And so you see we have two algorithms, tree-based and linear trainer. Here are the evaluation metrics of the tree-based trainer and the metrics of the linear-based trainer. As you see, the AUC is less than 50% in both models, so this is worse than random guessing. Yes, we should enhance this anyway. We cannot deploy or publish a model that is less than 50%. Because this means the model cannot distinguish between the two classes. The AUC of precision recall seems to be okay in both of the trainers, but we have to analyze this carefully using the precision and recall metrics. Here we have the positive precision and negative precision. The positive precision is good, but no wonder, really, because as you now know, this is the prediction of the majority class, and it's about 76% of the matches with at least one goal, so this is to be expected. And as said in the previous video, the real challenge is in predicting the negative class. The negative class is the minority class in our use case, which is about 100 minus 76 makes about 24% of matches without any goal. So this model can predict 23% of this 24% of the matches. So it's really not bad, not too bad as it might seem. Um, in the second trainer, we have zero negative precision. This means every time the model predicts that no goal would be scored, this is false. And look at accuracy, 76%. You might say, wow, but I will say for you, no, this is misleading because you don't consider the negative precision. Although the accuracy is better than standard, the standard is 70% in the theory, but as said, every time the model predicts that no goal will be scored, it's false negative. So we have a high accuracy, but without negative precision. In this sense, I can say that this model is better than this one, although the accuracy is worse, because this model with this worse accuracy can at least predict 23% of negative class or of the matches that would have no scores. And now you see what I mean in the previous videos of this series. Don't count on accuracy every time in every model. It depends. It depends on what you want to predict. What is the most important thing for you? Now let us use AI, for example, ChatGPT, and ask how could we optimize our pipelines, our trainers, um, regarding AUC, so we can distinguish between the two classes, and regarding negative precision, which is the area of interest for me at least. In ChatGPT, I copy pasted code you already familiar with. So here is the base pipeline with the known three columns or three features and both of the trainers. And the question is to analyze this and consider removing team names. Yes, you read it correctly. I would experiment with our team names, but only with the derived feature from the odds. And I ask also how to solve the negative precision problem of 0% weighting class as example. So we add a weight column for the model, and I give ChatGPT the majority class percent, so the HT goals distribution. And here is how ChatGPT replies. You have two categorical features which are one hot encoded. You also have a numeric feature and two pipelines, cross-validation results, and observations, negative precision 0% for linear model. This means the linear model never predicts the minority class, which is no goal in your case. Likely cause, class imbalance. One hot encoding of team names can dominate linear models, leading them to memorize high frequency outcomes rather than generalize. Linear models struggle with many sparse categorical features, especially if some team combinations almost always result in the same outcome. Now about tree-based model predicts. Tree can handle sparse categorical features better because they can split on individual team features. That's why negative precision is not zero for fast tree. It's able to learn some patterns for no goal. Accuracy paradox. In the linear pipeline, we have a better accuracy, but as said, it's predicting the majority class most of the time. In the tree-based pipeline, the accuracy is 67 or about 67%. It sometimes predicts minority class, so the overall accuracy drops, but the negative precision improves. This is expected in imbalanced classification, which is the case we have. Now about impact of team names. Linear models, one hot encoding team names can overfit on training data. For example, if team A often scores, the linear model assigns a large positive weight. This leads to this, that the model may never predict no goal. In the fast tree or the tree-based models, they are less affected with the team names because they can create splits like if home team is A and away team is B, one goal. Now about how to solve the negative precision problem in the case of the class is imbalanced. We have option A, use class weighting. We define a weight column in our model and assign it to the example weight column name property of the binary trainer options. And how we calculate it, assign higher weight to minority class. The linear model will be forced to care about minority class. This is the sentence to take with. We have further two options. I will not consider them for now in this video. And that's it. Recommendation for linear models, remove or encode team names numerically. We already encode them, so we will yet experiment with removing them. And then add class weights to force negative precision more than zero. And this was the theory part. Now to hands-on in Visual Studio. First, let us start once more without any changes in order to copy the metrics from the console in Notepad++. So we have one place where we copy paste the metrics from the experiments, and we can compare it easily. I have here in Notepad++ evaluating the evaluation metrics and now we start with omitting the categorical features. Now in our pipeline, we just have one feature which is based on the fair odds, on the probabilities of the odds. And we start again, and let us see how the metrics now look like. I copy it and Notepad++ without team names. Now we don't have the categorical features. And the first thing we get here optimized is AUC. In both models, it's now better, and the other AUC of precision recall is also a little bit better in both of them. And the negative precision is now worse in the first and still zero in the second. So now let us. So what is the what we have optimized here is only the AUC. Now about the weight, I define a property of type single. You can define it as float, and the name is the standard name is weight. You can give it the name you like, and the value is if the match has at least one goal, which is the majority class, the weight is one, so means uh, it gets no weight. But if the match has no goals, then the weight is 3.3. Where the number comes from? If we divide the number of matches that have at least one goal, divide it by the number of matches without any goal, we get 3.3. Let us start with this number. We will change it to 3 and 2.8 later to check what just to experiment with the weight and what does this mean. Now we have our weight and we need to add it to the trainer. Let us experiment with the linear based model. So I will come to this later. Now we just have in the logistic regression trainer, we here with parentheses, you see we have these options, the example weight column name and the regularizations later. But now for the example weight column name, we say that the column is called weight, and now give it a try. So I copy this. This was without weight, and now with weight. First experiment 1 to 3.3, and in the second experiment we give it a 3. Why? Because as you see here we have a downgrade in the positive position because the weight is too much. The model is now does not predict the positive class properly, so we reduce the weight a little bit and give it a try. And paste it here. Now we say with weight 3, 1 to 3. You see that the AUC is the same. The positive precision is good again, but negative precision not. The accuracy is also good. Now let us try the other weight, 2.8. What happens? So we get again the negative precision 0, so we don't need to compare this one. We we end the experiment with weights, and now for the regularization of the weights. Regularizations, we have two types, L2 and L1. The L2 only shrinks weights, and this means we get a dense model. L1 kills them, kills the weights. We get a sparse model. In the context of betting, predictive power comes from small effects. So let me say that the noise becomes an important signal. Every small difference in the predictions in the betting odds is important for predicting the number of goals. So we say that so we don't let the L1 kill them. Therefore, we set it to 0. You can experiment with a very small number, which removes only extreme noise. The standard regularization is 1, which is very strong in both. Um, so here we reduce it a little bit, still strong, so, and we give it a try. With weight 1, 3 and regularizations. So now look at this. The AUCs are very good. The negative precision is the highest value we could get for now. Positive precision is also good, and the accuracy is also good. Although we don't care about the accuracy, as said, we care about negative precision. But now we have a model that all of the metrics are good enough. We could deploy or publish our model if we build a program that you could let users use it. So this is very, very good. And I would ask AI about the meaning of the weights and regularizations. So this helped me to clear it for you. I simply paste it without any questions. Let us see what it says. These numbers show exactly how weighting and regularization interact in linear model with sparse categorical features. Let us analyze them carefully and then derive clear rules and next steps. What your results are telling you, baseline fact, important, majority class, and any model predicting mostly goal will sit near 76 accuracy. So accuracy alone is not a success metric here, which I say all the time. Your real problem was linear model collapsed to majority class, and the next precision was zero. You fixed that. Now we optimize that trade-off. Interpretation per experiment. Weight 1, 2, 3, 3. There was a positive precision, negative precision, and accuracy. What happened? Model is over penalizing false negatives. Over penalizing false negatives. It aggressively predicts the minority class, the no goal, which um, I this was not my goal to aggressively predict it, and massive accuracy drop because if the uh, if the majority class drops, of course the accuracy will drop because the majority class is majority class. Diagnosis. Decision boundary shifted too far. This is expected when class weights uh, nearly inverse class frequency. Useful if missing a no goal is very costly. So if you would hit live in a program or in web uh, only in no goals, so you could do this. But if you want usable predictions. Now with the experiment weight 1-3, what happened? Model starts reverting towards majority class. Negative precision is more than zero, problem technically solved, but negative precision is still weak. Linear model still dominated by one hot team names, correlated features. No, this is not true. Yes, ChatGPT does not have this information that I omitted them. Weight helps, but coefficients are unstable. That's a half fix. Yes, I know. Thank you. Now weight 1-3 regularization. This is the breakthrough result. Why this works? Regularization suppresses noisy team name co coefficients, prevents single teams from dominating the decision. Class weighting forces attention to minority class. Result, negative precision jumps, accuracy remains stable based AUCs. This is the first configuration that is actually healthy. Why regularization was the missing piece? Why the regularization was the missing piece? Your feature space is thousands of sparse one-hot team features, one numeric probability feature. Without regularization, linear model memorizes teams, but we have also omitted them. Some team coefficients explode, Minority class signal gets dropped. With regularization, coefficients are shrunk. Decision decision relies more on general patterns. Minority class becomes reachable. This is a classic linear model plus one hat encoding problem. About removing team names, very important. Yet now it comes to this. If you remove team names entirely, expected effects uh, PPs down, slightly downgrades and negative position upgrades further stability and model generalize better across seasons. For linear models, often improves minorities recall, reduces overfitting, loses team-specific bias. Yes, we now we have a model without team names. I strongly recommend testing this features fair prop only. Yes, we already have done that. And it suggests to alternatives from removing them instead of one hot team names, replace with numeric encoding examples, home team average goals. Yes, this is another topic where we could or one could calculate numerical informations from the Premier League and add it to the pipeline or to the feature engineered class. Key takeaway rules important for linear models with categorical teams. Never trust accuracy alone. Class weighting is mandatory. Regularization is non-negotiable. One hot team names are dangerous. Prefer numeric team statistics or remove team names entirely. This might be a longer video, but I hope you will find the information useful and easy to follow. I would really appreciate your feedback. Let me know in the comments what you think or what I could improve. Thanks for watching.